Welcome everyone to the first Statistical Mechanics seminar. As you can see, we are doing this virtually in a bit of a strange online environment. If you're interested in learning more about this, I won't go into it now, seeing as we're starting a little bit late. You can ask me after the talk. This is the way to join these seminars online. For those of you I haven't met, my name is Rohan. I'm a new PhD student here in the School of, or Department rather, of Electronic and Electrical Engineering, looking at sort of some deep learning stuff, some physics simulation stuff, and things like that. And this seminar is on statistical mechanics. Statistical mechanics was first developed as a theory of thermodynamics. And it's since been applied to a number of other problems in physics. And people have also recently been using statistical mechanics, mechanical ideas and sort of approaches to non-physical domains. And really that's the real focus of this system. Although if we're talking about statistical mechanics, there's really no way to get away from physical analogies or physical examples as well. People have used statistical mechanical ideas in statistical inference and Bayesian inference and in information theory. So more specifically, there's some sort of statistical mechanical formulations of ideas related to compressed sensing, which might be interesting to some people within the room. The statistical mechanical approaches to looking at constraint satisfaction problems when these sort of things are solvable and when they're not. More close to my area of research, it seems like people have attempted to use statistical mechanics to understand neural networks and learning theory and things like that. So the goal of these seminars is, at least initially for the first couple of seminars, is to develop a foundation in statistical mechanics that lets us assess the validity and strength of these approaches. So in setting up statistical mechanics, we don't want to rely on the existence of physical quantities that physicists take for granted. So for example, we don't want to assume that there's this sort of idea of energy that we have. And our goal from this is we want to be able to assess whether these approaches are sensible and what kind of assumptions are embedded into these approaches that might be not explicitly stated or not obvious. For these seminars, I'm going to focus on examples that I'm interested in. So they will be mostly neural networks and statistical inference, and also on one particular type of physical system, which are granular materials. Which are basically a system of grains, or think like sand or something like that. And this is an example of a physical system which doesn't neatly fit into the sort of the usual statistical mechanical framework. All that being said, if you're coming to these seminars and you're interested in something else, you're welcome to volunteer to give a talk on it. It's not a requirement of attending these seminars, but if you want to speak in these seminars, whether you're online or in person, then we can arrange for you to give a talk. So get in touch. One other thing I'll mention before we get into the content of it, there's a seminar webpage which I think was circulated. It's circulated on the Discord for those joining virtually, and in the email that I sent around for those joining online. And for those in the room, you may want to join the Discord that the people online are involved in. So ask me about that afterwards if you're interested. Okay, so statistical mechanics is concerned generally with dynamical systems where we don't know the precise state of the system, but nonetheless we want to make statements about the behaviour of the system overall. So usually this is framed as a distinction between microstates. Right, so these exactly specify our system, but can't measure them. And in macrostates. And these are the things we care about, these. Right. So these macrostates encapsulate properties of the system that we care about, but they don't uniquely determine the state of our system. So a typical example, maybe the original example is a gas. So in the case of a gas, we have the microstates are the position and momentum of particles, which of course we cannot measure exactly at every single instant in time. And the macrostates are things like volume, pressure, temperature, etc. We're going to set things up like follows. So we have a set R, which we call phase space, which is the set of all states of our system. So if you like, the microstates of our system. And really for the purpose of this talk, it's probably fine to think of this R as just being Rn for some n. So for example, in the case of a gas, this thing is R to the 6n, where n is the number of particles, right? Because we have 3 position, 3 momentum coordinates for each particle. And our system is dynamical, so it evolves over time. For each state, whoops.
Apologies, I may have to leave.
Yep, that's no problem. So for each state in our system, we think about it as being a function of time, right? Although we usually suppress time dependence from the notation, and we'll denote time derivatives using a dot in the usual sort of physics way. And then to reflect our uncertainty about the true state of the system, we represent the true state as a random variable. Or maybe more formally, a sequence of random variables depending on time. And we denote the probability density of the true state like so. Cool. Any questions about that basic setup? Yep.
Is there any intuitive reason why it's called phase space? Will that come later, maybe?
Possibly, but I don't know it. Yeah. Also called configuration space. Phase space is less syllables, so I've chosen to go with that one for today. Okay. Any other questions? None on one? Okay. Okay, so we're going to arrive at our a tentative definition. So it's not really a definition, but I'm going to call it one. So a statistical mechanical system consists of a phase space R, dynamics on states in R, and a sequence of densities rho depending on the state and possibly on time. So one for each positive time or possibly negative time as well.
Are you looking only at the first order distributions then? The joint distribution between successive states?
Yes. So we have more to say on perhaps what you're getting at here is there wants to be some sort of coherence, right, with this, which is exactly why this is a tentative definition rather than a something I'm committing to. And yeah, this is going on to exactly what I was going to say next. So this is not really a sufficient description of a statistical mechanical system. Of course, there are a bunch of technical conditions I probably need to state, which are kind of boring. So like the density needs to be a differentiable function of time, et cetera, et cetera, et cetera. But as was raised in the audience in person, more to the point, the dynamics of the system need to be compatible with this sequence of probability densities. So if we have a trajectory in phase space, in some sense, these densities have to kind of consistently assign probabilities to these trajectories, right? The idea is that, at least as we're setting things up right now, the dynamics are deterministic. So if a system is following a trajectory, we can't have it suddenly become much more likely or much less likely to occur as we traverse along that trajectory. Rather than trying to be precise about this for now, what we're going to do for the remainder of this talk is look at some sufficient conditions that are commonly used in statistical mechanics to ensure that we have this sort of consistency property. And I think over the coming talks, I don't really have a good idea about how to state this in more generality right now than we will get into later in this talk. But it's something I would like to sort of figure out as I'm giving these talks. Cool. Any other questions on that from those online? Cool. So before we move on to discuss this, how we ensure this sort of coherence of probability densities, I just want to state one other common condition, so an independent condition that's imposed or often assumed of statistical mechanical systems, just because it will come up a bit, and that is for what it means for such a system to be in equilibrium. So a statistical mechanical system is in equilibrium, or equivalently, rho is stationary, if the partial derivative of rho with time is 0. And yeah, I just wanted to get this on the board now so we can talk about it later. Note that even if rho is a stationary distribution or the system's in equilibrium, rho of some state x still depends on time because of the dynamics on the states. It's just that it doesn't explicitly depend on time, right? So for example, the particles in a gas still move around even though the gas overall is in equilibrium. Okay. So one way of ensuring that the probability distributions of the states are consistent with respect to the dynamics of the physical system is to assume that there's no sources or sinks of probability mass in phase space. So that's what we'll investigate now. This, more precisely amounts to assuming that the density rho satisfies a certain continuity equation, which is what we're going to derive. This is the same equation that, for example, the mass density of a fluid must satisfy to ensure like local conservation of mass. So we're going to assume that there's no sources or sinks, and we're going to go ahead and derive and see how this continuity equation is derived now. So let V be a compact, what else do we want? Compact, non-zero volume region of phase space with a smooth boundary which we'll call S. And the probability that our system is inside this volume is of course given just by integrating the density. Notice that this thing, notice that this thing depends on time, even when the distribution is stationary. And we're going to think about the rate of change of this thing over time. So the net flow out of V is given by integrating. So we have this. We can think about if we're thinking about this probability flowing around phase space, we can think about. Oops, that's not spelled correctly. But the probability flux, right, is given by rho times the time derivative of the state. All good. Cool, and we can think about the flow into or out of this volume V by integrating this probability flux over the boundary S, right? So let n, say hat, be normal to S, I guess outward, the outward facing unit normal of the boundary S, and then this flow out is going to be the E surface integral of this flux, which by Gauss's divergence theorem is just the same as integrating the divergence of the flux over the volume. Okay. Now we're assuming that there are no sources or sinks. So move to the next board. We're assuming that there are no sources or sinks in phase space. So what that means is that the time derivative of this probability has to be, well, what it means is that the only way that this quantity can change is by flow into or out of the volume, right? So in other words, the rate of change of this probability is equal to the negative of this flow, because this is flow out. What we're integrating here, the divergence of the flux. Okay, and what we can do is we can rearrange this and move differentiation under the integral sign to obtain the expression like so. Right, but now this is true of every volume V in our space. So we arrive at the continuity equation that over all of phase space, whoops, this thing is true. Okay.
I think 0 should be on the previous one.
Yes, thank you very much. Cool. Notice that I'll just make a note that if our distribution is stationary, so this thing is 0, then this is just the same thing as the probability flux being divergence free. Now, if you're sort of familiar with these sort of dynamical systems, then you probably already know this, but I know not everyone here is. So the continuity equation can be thought of as expressing sort of a fairly strong local conservation property of some quantity, in this case probability mass, whose density is given by rho. And it says that not only must this quantity be globally conserved, but it can't be generated in one part of phase space and destroyed in equal measure in another part of phase space. So for example, you can think about sort of the mass of fluid moving around. You can't have mass appearing over here and destroying in here and still have mass being conserved in the way we really want mass to be conserved in that space, in that setting. But what I'll point out is in the case that, so returning to the case where this is the probability mass of states in some physical system, the continuity equation doesn't hold of all physical systems. We can sort of see that intuitively. So the typical examples of such systems which don't satisfy this equation are systems which dissipate energy. So in this setting, the mass or the probability mass of the system accumulates in regions which have lower energy. So as time increases, the system tends to gravitate towards regions of low energy and it abandons regions of high energy. And you can think of the intuition to have is that the regions of low energies are going to be sinks of probability mass and the regions of high energy are sources. We'll sort of make that maybe more precise, but maybe not quite as precise as you may want with an example, which I think I'll hope to return to in a future talk when we cover these types of systems in detail. So consider a ball rolling on the surface. This thing, right? So paraboloid, whose position with initial position randomly chosen according to some distribution, whatever you like. And the state of this system is just a point in two-dimensional space, right? Because it's sitting on top of the surface. Right. Now, if the ball is subject to friction, right? In other words, it's got some mechanism to dissipate its energy. Then as t increases, the probability distribution on the state of the ball will concentrate on the point 0, 0. So we expect 0, 0 to be a sink. Okay. We're going to cover, I plan to cover sort of dissipative systems in a future talk, but from what I understand so far, which is not everything, they're much more difficult to analyze than non-dissipative systems. So we'll park that discussion for now and move on to talk about some systems which do satisfy an important class of examples of systems which do satisfy the continuity equation. Before I go ahead and do that, any questions either online or in person?
I have one.
Yep.
Why did you? I didn't get the intuition. Why rho x dot is a floating flux intuitively?
Yeah. Which board was this? Oh, I'm not seeing. Is it on the board? I think maybe the previous one. Oh no, maybe it was on that one. So let's see. So x dot is the trajectory of the system, and rho is like its density. So it's proportional to. So a physicist would think about like literally a whole bunch of particles, what they call an ensemble. It seems like, at least the way it's written in the book I'm reading, it consists of a whole bunch of particles corresponding to different versions of your system, if you like, and then this density rho is literally just the density of those particles in that region of space, right? And if you weight that velocity by the amount of particles there, that gives you the sort of the flux, the number of the probability mass per unit time per unit volume, the rate in change in probability mass. Does that make sense? I don't think I explained that very well.
We should think of these x's of containing momentum as well, not just position.
Yes, yeah. So we'll get to Hamiltonian systems just coming up, but yes, it will contain momentum and position. Yeah, it's exactly the same. Like if this was like this was mass density, like actual density, then for a fluid, then this would be usually u is the velocity of a fluid, right? Then rho u is the mass flux of that fluid. Any other questions? Cool. Let's keep on going then. I guess we'll go over to the fourth set of boards, or the second set of boards, sorry. Okay.
Oh, no, then I think there's a speaker.
Cool. So now we're going to talk about Hamiltonian systems. I guess sort of for two reasons. So firstly, they're just all over the place when you read about statistical mechanics, so it's good to understand them. And secondly, I think Ben at some point is giving a talk on ideas related to these things, possibly in another seminar. So they are also related to sort of the more statistical inference kind of things.
Next week.
Next week, okay.
Looking at your slides, you wrote a lot of what I was going to say. So
well, I'm gonna breeze right through this. So so that's totally fine. Okay, so in this case, our phase space is going to be some even dimensional Rn. Oh, sorry, I guess R2n. And the state will, now we think about there being two types of coordinates. So we're going to have a coordinate Q and a coordinate P, right? Where P is in Rn, we think about as being momentum, right? And Q, also in Rn, of course, is going to be position. So yeah, now we're really thinking about a physical system, although you can kind of make analogies with, I guess, non-physical systems and think about them in this way, which we'll maybe cover in another talk or in a future version of this seminar. And we have a function called the Hamiltonian, which we denote as follows. So this is a real valued function. And in a physical system, this is the total energy of the system. And these coordinates are related by a system of partial differential equations using the Hamiltonian, which are as follows. So the time derivative of position is equal to the momentum derivative of the Hamiltonian, and the time derivative of the momentum is equal to the negative of the, this should be the position derivative of the Hamiltonian. Oh, P. And of course, there's a whole bunch of these. And the solutions to this set of differential equations give the dynamics of the system. What this is basically expressing is it's saying these position and momentum coordinates evolve according to the laws of physics. I won't go into why this, what a Hamiltonian is, or why this is true of the physical quantities of momentum and position. Just take this as given. Okay. So one example of such a system is the gas that we had from earlier, and then we might have the first three position coordinates, the position of the first particle, and the first three momentum coordinates, the momentum of the first particle, and so on. The next three are the next particle, and et cetera, et cetera, et cetera. Okay, if we assume that the particles don't have interactions with each other, then the Hamiltonian is just the sum of the kinetic energies of each of the particles and the potential energies of each particle as well. Okay, in that particular example. Okay, so now we do you want to just take a look at the next board? So now we're going to suppose that our density satisfies continuity, or the continuity equation. just shorthand for satisfies the continuity equation, which we derived before, and we're gonna see what that looks like in the specific case of a Hamiltonian system. And what we're going to arrive at is a named result, which you'll see if you start reading about statistical mechanics, called Liouville's theorem. So what are we at? So noting that the time derivative of space is now just the time derivative of position and momentum, we can start thinking about what the divergence of the probability flux is. And well, that is, this is just amounts to calculating things. So that is just going to be this. Cool. Stop me if I'm doing something silly. Love the product rule. Okay, and then we're going to regroup this as follows. So we are left with this thing, which is going to stick around. Yep. And then this last term, which I'll explain in just a moment, is going to disappear. Okay, so I claim that this goes away. That is because by the Hamilton or Hamiltonian equations, we have, oops, QI, that both of these things are equal to the second derivative of the Hamiltonian.
Sorry.
Oops, Q.
And I was just here yesterday.
Okay, so as a result, this whole thing is 0, right? And we are left with that this thing is equal to just this thing here, which is, I'm going to denote like this, not for no reason at all. It turns out this thing is equal to something called the Poisson bracket of the density rho with our Hamiltonian. You can check them. I mean, it's probably obvious from the definition what that must be, but you can check the notes that I've posted online if you want to see that written down. Okay. And then from here, we arrive at the famous Liouville's theorem. So really just, moving some sort of derivatives around and things like that, but it is named. So for a Hamiltonian system, the density rho satisfies the continuity equation, if and only if we have the following expression holding true. I'll skip that for now, actually. Okay, so that's sort of all well and good. The reason this is sort of somewhat significant is maybe not obvious initially, but this equation here is the equation for which defines the flow of an incompressible fluid governed by a Hamiltonian H, right? So you'll often see Liouville's theorem being stated or interpreted as saying that the density rho of such a system behaves in the same way or evolves like a fluid which is governed by the same Hamiltonian as the original physical system, right? So this is the sort of why people write down this theorem and care about it. One thing to note as well is that because if we remember what this thing looked like, this is actually also just equal to the total derivative, also sometimes I think called the material derivative, or though I'm not that familiar with the terminology of the density rho in the case of Hamiltonian systems. So it, which is I guess where the sort of idea that this thing is incompressible is coming from. Cool. Any questions about that?
What's the difference between partial and total?
So with the partial derivative, right, we're holding all coordinates in space fixed, and we're looking at how it ought to change at that particular point. And the total derivative, we need to apply the chain rule and think about not only if time is changing, will also the points, if you like, are moving, right? Because we've got some sort of dynamical system going on here. Cool. Oh yeah, and I'll point out if for the mathematicians in the crowd, this is mathematically unrelated to another Liouville's theorem. Both are named after the same mathematician, which says that every bounded holomorphic function is necessarily constant. There's no relation at all, just named after the same dude.
He proved two theorems.
What's up?
He proved two theorems, at least.
At least two theorems in his career. Yeah.
Wait till you hear about Euler.
Yeah, I know. Cool. Okay, and then just to wrap up today, so I might talk about, I'm going to talk about, well, we'll just jump straight into the lemma. But what this is sort of getting at is sort of that this continuity equation, or an equivalently Liouville's theorem, are satisfied under some pretty natural choices of rho, right? We haven't really committed to a choice of rho so far in this talk, but now we're going to see that the sort of the ones that you will likely choose, this is true of such a Hamiltonian system. So the statement of this lemma is if rho depends only on H directly, i.e. we have some function f such that our density can be written like so. I guess I've been using Q and P here. Then rho is stationary and satisfies the continuity equation.
So that's if it's like a Boltzmann distribution.
Precisely, yeah, that's where I'm heading with this. Yeah, I'll maybe brief. How are we doing for? No, yeah, it's good. I guess it's good, right, when your audience is anticipating what you're going to say next, right? So, cool. So I guess we'll just prove this, and then I'll talk about maybe why this is something worth proving. So the fact it's stationary is clear, and I guess the fact it is satisfies the continuity equation. Well, all we need to do is show that this Poisson bracket is 0, and this one just follows from the chain rule. I guess since we've got the time, I'll write it out. cool. I guess, yeah, we'll just keep going with this. And then this is just going to be the derivative of f composed with h. And I'm really giving myself a small amount of room to shove this in.
There's another one.
I want to get it in here. Yeah, if it's too small, then consider it an exercise, I guess. Right. This bit here follows from the Hamiltonian equations, right? So this derivative here is now becoming this. Oh, this possibly an error in the notes. I'll just keep going and think about if I need to fix it later. Okay, which is 0, right? Stuff that one in the end there. Okay, point is it's not too hard to prove. So this lemma shows that many common choices of the density row automatically result in this density having a really nice relationship with the dynamics of the system. And one common choice of density, as was mentioned in the audience here, is the Boltzmann distribution. So for those that haven't seen this, it's I guess a sequence of distributions parameterized by some parameter beta, positive parameter beta, which can be written as follows. Where z, called the partition function, yep, dx, I guess dq dp. We will probably talk about this Boltzmann distribution, so you can justify choosing the Boltzmann distribution via a sort of a maximum entropy argument, rather than stuffing it in the 10 minutes that we have left in this talk. I plan to cover that in a future talk. Why the Boltzmann distribution is something that makes sense, or maybe rather how I think about it, why what assumptions go into choosing the Boltzmann distribution.
Because as long as it's a constant temperature.
Yes.
It's the inverse temperature.
Yeah. So beta is inverse temperature. Yeah. Cool. Cool. That's about all I had for today. I guess the takeaway from this seminar should be, to sort of start thinking about what are the essential components of a statistical mechanical system. And I think the real takeaway is, we need this relationship between the density or the probability density on states and trajectories as determined by the dynamics of the system. And that will, as we might expect for a whole bunch of statistical mechanical systems that people, spend a lot of time studying, all of this happens essentially automatically due to the nice properties of Hamiltonians and the fact that we choose Boltzmann distribution and things like that. But then in future talks, we'll build on this and maybe start to talk about some systems which are not Hamiltonian, or maybe don't even satisfy the continuity equation, but hopefully still consistently assign densities to trajectories in space. Cool. Thanks, everyone. And if there's any questions, then go ahead.